Welcome everyone to Data Structures and Algorithms. In this first lecture, we are going to explore the master roadmap of this course using our interactive mind map. This diagram acts as our compass, showing how every topic we study over the coming weeks connects to form a unified problem-solving toolkit. At its heart, our course has two primary goals: learning how to systematically organize our data and learning how to write highly efficient algorithms to process that data. Before we look at structures, we have to ask, what is data? Simply put, data is a collection of facts from which conclusions can be drawn, whether that facts are textual, numeric, audio, or video. A data structure is the representation of the logical relationship existing between these individual elements. Programming languages give us basic primitive data structures like integers, floats, characters, and booleans. But to solve complex computing problems, we must group these into non-primitive structures, which we broadly classify as either linear or non-linear. As we travel down the linear branch of our roadmap, we'll encounter structures where elements exist in a sequential relationship. We start with arrays, which use consecutive memory locations, but quickly discover their limitations in size and flexibility. To overcome this, we'll design linked lists that grow dynamically in memory and specialize them into stacks, operating on a last-in, first-out basis, and queues. Panning across to the non-linear branch, we break away from sequential lines. Here, we'll master hierarchical structures like binary trees and heaps, which allow for incredibly fast searching, insertion, and deletion. We will also explore graphs, which allow us to map complex networks of relationships without any strict hierarchy, paving the way for advanced navigation and communication algorithms. To build any of these structures, we first need to master the underlying system mechanics. We'll start by exploring pointers, variables that store the computer memory address of other variables, and C++ structures, which let us group heterogeneous data types together. This forms the basis of abstract data types, which are mathematical models that specify what operations a data type can perform while completely hiding how they are implemented. But writing a program that works is only half the battle. We must also write programs that are efficient. How do we measure efficiency independently of the specific computer or programming style we use? We use theoretical algorithm analysis. We will count the number of significant operations in our code and express their efficiency as a growth rate using big O notation. Together, we'll analyze how our algorithms behave in the best, worst, and average circumstances, comparing simple linear operations to logarithmic scales and quadratic loops. This mind map represents your journey over the semester. By the time we reach the end of this roadmap, you won't just be writing code. You will be architecting elegant, highly optimized software systems. In our next segment, we dive straight into our first core building blocks: pointers and structures. Get ready, and I will see you in the next video.